All right. Good morning, everyone. Thank you very much for coming. My name is Tobias Preis. I'm one of the faculty fellows of the Turing Institute, and I'm also an associate professor of behavioral science and finance at Warwick Business School, actually formerly trained as a physicist. At Warwick Business School, I'm directing the data science lab together with my colleague Susie Mote, who is also here in the room today and also a faculty fellow. And we are extremely happy to also be able to have brought over to the Turing Institute two of our excellent PhD students, Shanuki Sarasinya and Marva Alaniel, who are also here today. So at Warwick, we are looking at data to sense human activity in the real world. I don't have to tell the audience in this room and beyond what this actually means nowadays, given our increasing interactions with large technological systems like our smartphones, from just calling a friend for a chat, taking a ride on the tube, or just buying bread in the supermarket. So all of this is now generating data, lots of data. And what we are keen to do is actually using these traces of human behavior, so what people are searching for online, let's say on Google, information they share on Twitter, Flickr, Instagram, and so on and so forth, in order to look into human behavior. What is the advantage of these new data sources? So on the one hand side, these data sources are global. These data sources can be extremely fast. I mean, most of them are almost immediately accessible after they have been generated by us. And they can be very cheap. So some of them actually coming for free just with a direct access via an API. So at Warwick, we are using data sources like these in order to tackle three objectives. And these three objectives, basically, we are keen to bring to the Turing Institute, and also basically using these three objectives to basically opening up discussions with as many of you as possible in order to take them to the next level and to foster collaboration across this very interdisciplinary space. So what are we trying to do with these data sources? We use the very fast nature of these data sources in order to reduce costs and delays when measuring existing data, existing measurements about human society. This can be the case when, for example, existing measures are delayed due to the nature how they are collected and how actually the collection and aggregation procedure, data cleaning procedure are putting together an entire data production chain, which is slowing down, for example, the announcement of unemployment rates. On the other hand, these new data sources are opening up to measure new quantities of behavior, things like well-being we haven't been able to tackle before at all. When we know a little bit better what is going on in the world right now, because we can measure it quicker, then in some cases this might then open up possibilities to look into future behavior of at least of a group of people, what they might do, for example, in an urban context. So these data sources, I'll quickly run you through a list of all the Instagrams, Flickrs, and Twitters, and so on and so forth. So what does this actually mean? What is the data looking like we are keen to analyze? So this is an example visualizing the locations where 35 million photos of the photo sharing website Flickr have been taken and subsequently uploaded during the year 2014. Very easily, very quickly, you can realize and see that the shapes of the continents are emerging. You can get an idea about the potential biases of these data sets. Not necessarily the entire world is captured in an even way. And this kind of bias becomes further down the line even more dramatic if we look into changes over time, changes in human behavior, which I will come back to towards the end of my talk. So what I would like to do in the given time which is available here today, I would like to run you through three examples of our recent research, which I hope will try and stimulate these discussions, where this might actually be able to contribute to something further in the near future here at the Turing Institute. So we were particularly fascinated by the possibility to study what people are searching for online. Never before have we had an opportunity to analyze Google search behavior, for example. So within this stream of research, basically looking at many different examples and data sources, I would like to focus just on one individual small piece of information where we tried to link search behavior on Google to what is going on in the stock markets. So in this very first case study we looked at, we analyzed how often people search for a particular topic or term in a given week. We looked at how this relates to past behavior. We're just interested in the question whether more or less people are searching in a given week for a particular topic or term, and made, based on this, decisions, hypothetical decisions to act in the markets during a certain time period. For example, if the volume for a particular term dropped in a given week, we triggered a buy transaction in the underlying market, doesn't matter who this was at the moment, and basically kept this position for 1 week, made profit when basically the underlying index went up over the time period, and the opposite scenario when more people have been registered to search for this particular term, then we sold the market and profited when the market went down during this 1 week's period. So what is the result of this simple case study? We looked at a range of different terms, for example, how often people searched in the US for the term culture. When we actually plot this over time for the time period analyzed, 2004 until February 2011, we find that for culture, if you plot the cumulative profit and loss over this time period, you wouldn't have resulted in much more than you would actually expect by chance, in particular when you compared to what would have happened if you just bought the underlying index, Dow Jones Industrial Average, and would have kept that position over time, 16%. You actually can clearly see that these boundaries, which visualize the ±1 standard deviation of just randomly trading every week, basically frame these two curves, visualizing or showcasing that there's not necessarily something very interesting going on. So we looked at a range of different keywords. We looked, for example, also at how often people search for debt and how in this given trading framework such a keyword would have performed. There, the analysis outputted a slightly different picture, which then led to the key question: can we actually look across the space of different keywords we analyzed at a certain feature which maybe makes these different keywords successful? So we looked in fact at 98 different keywords. Debt and culture were amongst them, and we were keen to construct this set of keywords in a way that it actually reflected to some extent financially related keywords, but also random keywords like culture, garden, train, and so on and so forth, in order to be able to have a certain space of variance which might allow us to dig out certain patterns we would have been able to identify in that time period. So for example, stocks and credit tended to be on the left-hand side of the spectrum, generating a profit larger than zero. And on the right-hand side, yeah, if you look at this, then basically the idea could be that the more randomly generated terms were the ones which didn't produce any meaningful profit within that hypothetical trading framework with all its limitations. And so the question arose whether this is actually a feature we find and can quantify across this topical space. And so we constructed an index which we call financial relevance, which is simply defined by the number of occasions we find these individual terms in financial literature. So the idea was the more this term is used, for example, in the FT, in the Financial Times, then the more financially relevant this term should be. We had to normalize for the fact that obviously the Financial Times is written in English, and we had to then normalize by all the hits, for example, which Google finds in order to get to remove all the n's and the and so on and so forth, just commonly used words in English language. It turns out, or it turned out in this initial case study, that there was a significant correlation between the financial relevance and the profit we found over this time period. I have to leave this stream of research there. There's much more which could be said. I mean, we looked at different stocks, individual stocks. We looked at different time periods. We looked at increasing markets, decreasing markets. and all sorts of different other features which might influence that behavior, but this would be a subject for a longer talk. Instead, I would like to move on to a second example where these new forms of data can actually help us to tackle age-old problems. And one of these problems is actually the question of how many people, for example, are protesting, how many people form a crowd. So traditionally, or amongst the still commonly used methods, is actually to take visual footage of an area, for example, people demonstrating in the streets, and then gridding this photo into certain areas, counting how many heads we are able to see, and multiplying by the number of cells. We thought, given the ubiquitous of information nowadays available via electronic devices, and paired up with the opportunity that one of our fantastic PhD students, Federico Botta from Italy, was able to get hold of such data sets for a city in Italy, Milan in fact, we wondered whether this information can help us to calibrate these new forms of data with the question how many people are in a restricted space. So in fact what we had were 2 months of data back in 2013 for the city of Milan for 235 meter squared cells for 10-minute intervals. For this time and space windows, we had information of how many mobile phone connections have been opened, maintained, and closed, how many SMS messages have been sent, and how many internet connections during the same time actually have been established. On top of that, we were able to compare this information with all the tweets shared during the same time period for the space of Milan. Coming back to the problem. So how to count people in a certain space? It basically reduces to a problem where we want to know how many mobile phones, active mobile phones, compare to how many people in a certain area. Given the data, we had to find examples for which we are able to calibrate the signal. And together with Federico and Susie, we ended up finding this cell of 3 times 3 subcells, which is the area which overlaps with a football stadium. For this area, we were able, at least afterwards, to access how many people have been at a certain game, because this information is public or published afterwards. So what you can see is here is one snapshot for 22nd of December 2013, where you can see people arriving at the stadium, and these 2 vertical bars indicate the 2 halves of the game, basically showing that this drop towards the first half or beginning of the first half of the game, then an increase between the 2 halves, opening up all sorts of possible interpretations about the interestingness of the game, or maybe the capacity of the mobile phone network not longer being able to deal with the number of connections. So how does this signal then compare with the data which we got afterwards about how many people attended the games? This bottom layer here shows you the officially recorded number of attendees compared to the 3 layers of information we got from the mobile phone network and from Twitter. Visually, very nicely, you can see that these peaks align, but the question is, how well do they align in terms of size? When we plot the information against the officially recorded number of people coming to the stadium, then we find that for all 3 of them on the left-hand side, A, B, and C, there's a very close match. We are talking about adjusted R-square values of around 0.8, 0.9. And you could ask the question, all right, so what is then actually the best signal amongst the 3 different sources? And surprisingly or not so surprisingly, it turns out that the internet activity, so the number of internet connections opened, maintained, and closed, seems to be the best estimate. And when we think about that, then this actually makes sense. Whilst you are sitting here in this room, all your mobile phones are making little small calls to server centers, downloading emails, maybe apps are updated in the background, you're not necessarily actively using or interacting with your phones. So this answers the question, which is the best data set for estimating how many people are there? But how well are we actually doing? So during this 2-month period, we had the chance to look at 10 different games. And the question was, if we use 9 of these 10 games in order to train our model, how well is actually our estimate, how accurate basically is our estimate for the 10th game? And we find that the mean absolute error for such a setting is around 12 to 13%. So now the question is how good is actually 12 or 13%? So if we look at examples, historic examples, where people tried to estimate the attendance of large protests in the world, for example, the Million Man March in Washington, D.C. is one event people commonly refer to in the 1990s, when people demonstrated for the right for Afro-American people in the US. So there actually, after weeks of estimating and looking at visual footage by experts from Boston University, they ended up with an error of around 20%. And again, to put it into context, this is information only retrieved after a certain amount of time, while such information would be accessible almost immediately. A final note, that actually this information on the left-hand side, A and B, is obviously something which is proprietary data, which is basically collected by the mobile phone carrier. However, we are almost doing as well with publicly retrievable data, which comes from Twitter. So this brings me to my third example. And in this third example, we need to look at what I started to say at the beginning. All sorts of ratios we retrieve between online behavior and behavior in the real world comes at a certain cost. You need to make assumptions about biases. You need to try to learn and deal with these biases in the best possible way. And this third example is, to some extent, classic example, where over time, this actually went dramatically wrong. Let me please remind you of the Google Flu Trends example, when back in the days, in 2008, 2009, Google engineers teamed up with the Centers for Disease Control in Atlanta, being tasked or given the task to look at how many people in a given week have influenza-like illness symptoms. So that's something the Centers for Disease Control are routinely producing, these figures. And the question was whether quicker data from Google might be able to fill in a time delay gap, and this gap is up to 2 weeks, because the Centers for Disease Control are asking a network of doctors all over the US a simple question: how many influenza-like illness symptoms patients have you seen over the past week or so? This information then gets collected from this network, processed, and when finally the CDC in Atlanta has this final number in order to make maybe very difficult decisions, maybe to close down airports because of the severeness of the problem, then this number is up to 2 weeks old. So when Google looked at this and finally then correlated all possible search volume time series with this weekly number of influenza cases, then they found out the top correlated ones, that's a very striking pattern. So the most correlated search terms, all of them, were actually symptoms which you would expect to maybe Google if you have the flu. So it was a paper published in Nature. It was turned into quite a success. I mean, it was rolled out in a system used in many different countries. Yeah, until the service didn't work so well anymore. So what has happened at that point in time? So during the winter, 2012, 2013, this Google-based estimate, taking into account how many people search for these 20, 30 different search terms, dramatically overestimated the real number of people being ill. Why was that the case? Experts put many different reasons for that. Amongst the most commonly cited ones was actually the fact that during that winter, a new stem of the flu, H1N1, occurred, which, via media reports, possibly triggered many people to search for symptoms just because they were scared rather than actually being ill. There are all sorts of other reasons which you could add to this. Obviously, search engine algorithms are not constant over time, and behavior is changing over time. There's also little small info boxes which you can see in the US if you search for flu symptoms. And so there are all sorts of things which change over time, which might affect and seriously have affected this estimation method, which was based or is based on an algorithm or basically a simple correlation back in 2008, 2009, assuming that this stays constant. It didn't. So from that point of view, many people raised the issue, is this maybe the end of this entire field, what people call computational social science? I mean, if you can't use this reliably, I mean, what is the value of these new data sources? And a number of people, colleagues of ours, but also Susie and I, looked into this a little bit more carefully. So we have these correlations with search terms, but we have also the information how many people actually are ill, or to be more precise, how many people were ill 2 weeks before. This original model proposed by Google together with the CDC didn't incorporate the 2 weeks delayed information and assumed this to be constant over time, the relationship between the proportion of people Googling for symptoms and the proportion of people being ill. So if we combine all of this into a model where we basically have a baseline model, which is just a simple autoregressive model taking the past information into account, and add, in addition to that, as an external regressor, the search volume data as retrieved from Google, as one part of the solution, but secondly, specifically address the issue of changing behavior, in particular changes to external, for example, media reports. When we include this in a way that we have a running window through this entire time suite in which we relearn, recalibrate on an ongoing basis, this relationship, the portion of people searching for these symptoms and the portion of people being ill, because basically we get updated values for the actual people or the number of people actually being ill, it's just 2 weeks delayed. So when we do all of this, then we are able to show that there is still value in the fact how many people search for these flu symptoms. So we are able to reduce the forecast error significantly compared to a baseline model without the Google search volume by around 16 to 53%. The range is due to the fact that obviously you can use different sizes of windows which you use in order to relearn that relationship. So it's not necessarily the data which is sometimes the problem due to changes or problems with biases. It's a question of finding the right way to analyze and incorporate these new forms of data into our models in order to make them work, in order to be able to reduce delays in measuring what is going on in society. I would like to close with that, and I would like to restate that we are very keen to talk to as many of you in order to find ways to use this fantastic cross-disciplinary experience of the Turing Institute to take maybe some of these ideas forward, or maybe in some ways these data sources and approaches can be used in order to take some of your ideas forward and to find ways in order to make that work. Thank you very much, and I'm looking forward to any questions you might have. Yes, please.
That was really interesting.
Thank you.
I'm just thinking about some of the ethical considerations around basically pulling people's data who unwittingly are aiding these models. I mean, do you have any thoughts on that?
That's a brilliant question, and obviously a question not only we in this room, and basically we as society need to address that point. So let me stress one aspect of that. So all the, except the mobile phone data, so all the analyses I have presented today are based on data which is publicly retrievable via APIs. And most of them, I mean, obviously Twitter is a different story, but most of them also are based on aggregated information rather than on data which is just about individuals. However, given that some of these sources obviously reveal data about individuals, like Twitter, you are able to retrieve individual tweets. I mean, it's a public source on the one hand side, but I agree with you that it's not only the question about making these data usable in one or the other way, it's basically also an agenda for us to make society aware of the possibilities and maybe potential pitfalls where this might be a problem. For example, Susie and I, we are running a massive open online course on FutureLearn for big data analytics, actually explaining some of these examples, where we actually are keen to raise the public awareness of what is possible with these data sources in order to create, in order to make people think about this carefully and critically in terms of which information they are revealing about themselves. Yes?
I would like to know what kind of mathematical and statistical techniques you're using to do your data analysis. Is it existing work or are you developing new tools?
That's a very good question. So basically it's a range of different methods, and it's basically problem driven. So it can be as simple as a correlation or a simple regression line if this solves the problem. It can be as complex and complicated as a convolutional neural network when we try to retrieve information from actual images rather than actually relying on metadata or description fields of this particular image. So from that point of view, that's another key area where we are extremely excited to work with as many as you, where we can take on board new machine learning techniques being developed here at the Turing Institute. And that's basically the simple description of the range of different methods. I mean, again, let me restate, it's actually problem driven. All right.
Sorry, you want to ask one question? Do you know, have you thought about how this could be implemented to like trading strategies?
Yes, okay.
There are hedge funds that basically do a lot of what you're doing.
Okay, I think I have around 60 seconds to answer your question before we actually run out of time, and there are people agreeing to that on the left-hand side, being stressed about the schedule. So let me very briefly say something about the applicability of these things in the real world. I mean, as I just said, we're looking at problem-driven aspects, and we're very keen that actually these methods are used in the real world and change something in the real world. I mean, for example, we work with the Office for National Statistics here in the UK, who are using some of our methods. For example, this background photo around images in order to look into travel flows in the UK, but also around the world. But also the example you raised before, I mean, obviously lots of banks and investment institutions were very keen and contacted us after we had published this paper and then also a sequence of other papers afterwards. So for all these different examples, we are actually very keen, and basically in the first instance, these are the motivating aspects to look at a particular case that we are actually able to change something in the real world. All right, thank you very much.